doesn't really give the same, it doesn't really give the same results, which means that it cannot be relied upon. So that is one of the gaps that needs to be breached, just so we can make this a little bit much more feasible for the farmers. For our study objectives, the most important part of the study was to evaluate the impact of lighting conditions or lighting variability on pharmaceutical image classification. Also, we collected or we compared two models, the SVM and the BPNN. In this case, the SVM was chosen and the BPNN, they were both chosen for specific reasons. The SVM was chosen because the SVM is a simple classical machine model, while the BPNN is a much more complicated neural network. So these are two very different models which we compared. So those are one of the reasons why we chose to compare these two different models. For our data sets for this particular research, 1,000 pharmacia images were collected out in the farm. To be able to eliminate bias, we also balanced the set by dividing them into two groups, shaded and unshaded. And also we further went ahead to distribute them across 5 classes, pharmacias 1, pharmacias 2, pharmacias 3, 4, and 5. Now this helps the machine to not learn spurious associations between lighting conditions and health status. Now, usually when we get images from the farm, there is a noise that has been introduced because of the real world environment. So when we take these images back to get them analyzed, we have to eliminate that noise. We also do tend to increase or adjust brightness and contrast, and we also add a few also minor adjustments to it as well. This data processing procedure or this pattern helps us to balance the sets in the sense that this helps us to focus plainly or specifically on the effects of lighting conditions on pharmaceutical image classification. For the two models that were tested, we used the SVM and also the BPNN as well. Now, the SVM machine generally focuses on maximizing class separation. The BPNN, on the other hand, is a nonlinear pattern. It's a model that models nonlinear pattern, but it functions better with larger data sets. And the SVM, on the other hand, performs better with smaller data sets. This evaluation helped us to compare the model complexity versus robustness. For our evaluation, we used the tenfold nested cross-validation. Now, the reason why this was used was because the tenfold nested cross-validation system, the tenfold nested cross-validation system helps us to access, it gives us an unbiased estimate as how these models will perform when deployed in the real world or out in the field, which is why we use the tenfold nested cross-validation. The inner cross-validation handled the hyperparameter tuning, and the outer loop handled the performance evaluation. This helped reduce overfitting and helps give us a good estimate as to how these models will perform out in the farm. For our results, our SVM achieved a peak accuracy or performance of 98% with a precision of recall of 0.98. It also had a Cohen-Skapper score of 0.959, which shows agreement beyond chance, strong agreement beyond chance and shows that the SVM model performs better in terms of robustness at the farm. Also, the BPNN achieved an accuracy of 97% with a precision of recall of 0.94 to 1, and a Cohen-Skapper score of 0.939. And it also shows some variability across validation folds. So that means that the BPNN was highly sensitive to lighting variations during the study compared to the SVM. Now, for our findings for this particular study, we found that the more complex models sometimes does not always do or perform better than the simpler models. In this case, the SVM, which is a simpler model, performed better than the BPNN and showed a lot more performance and gave a lot more robustness out in the farm. The reason for this could be that the SVM was fed smaller data sets than the BPNN, which was fed smaller. If you remember, we said the BPNN performs better and gives a consistent performance if fed more data sets. But in this case, we use 1,000 images, so that could be why the SVM performed better. For our conclusions and moving forward, we found out that lighting conditions significantly influence AI-based Fibonacci image classification performance. We also, SVM demonstrated greater robustness on the variable illumination compared to BPNN. And the findings support the feasibility of field-ready ML-driven Fibonacci tools, which means that in this case, since we used the SVM and it performed really well, and the accuracy gave us a score of 98% and a very good performance, it could be tested out in the field just for a test run. So that was one of our findings. Also, for the future work, we're going to be adding different models to it. We're going to be examining not just the subject vector machine or the support vector machine or the backpropagation neural network. We're also going to be examining and adding the CNN's network as well, the convoluted neural network. Our long-term goal for this particular research is to make sure that farmers can accurately check for Fibonacci scores in the farm without any sort of subjectivity, trying to take away that maybe from them. This can improve animal health, which can also improve farm productivity, and also it can reduce unnecessary deworming of the animals, which can also reduce antimicrobial resistance, which is a huge public health concern. So this is very important for our study. So that's what we're looking to do with this particular study. Thank you very much. If you have any questions, please, the floor is open for questions. Thank you very much.